Okay, great. Welcome, everyone. Good news. I think we managed to clear the wait list. So this is the first time in 4 years that we manage it, and in big part because of the spring version of the class. So I think we're now stable capacity-wise, it seems. We may be able, there were a few requests for auditing, so there may be, we cannot go more than 100 because of the class, but yeah. So if you email me previously for auditing the class, please email me back. I think tomorrow we should be able to get a few people there. So this is perfect. 100 is what we were hoping for many reasons. First is to be sure that we have a primary TA for each team really working with you closely. And second, the midterm presentations will be in person here. And so to be able to fit all teams in 2 sessions, we cannot have 50 teams. So there's a little bit of constraint on that. So we have a few administrative things. So we're changing, we're grading descent, where we're going from 8 p.m. We're going to try 9 p.m. And see if it's a local maxima mode of it. And if needed, if we get feedback, we increase. The other, the loss function has many terms. One of them is how much time we give the prompt feedback on the questions that you ask as part of the form. So that's also why we're optimizing that. We're hoping to start that process in the evening, set the things also. So we're trying 9 p.m. We also optimize the process to post the lectures on Panopto. So hopefully it will be faster. Just if there's delays, we'll adapt. And thank you for your understanding. Don't forget, I will have my phone ringing also. There's 3 sessions. So take notes, what's interesting in this session, but also bring as many questions as you can, please. There were only a few questions. I know it was these are kind of an introductory lecture, so there may be not as many. One thing I didn't put a slide for that, but one question, because I know the fast RNN came a little bit quickly at the end. So maybe I can just give a high-level intuition. If there's more question, I could go back to the slides again. But the general idea is that if you train a CNN, what are you training? The only parameters you're training are those templates, those kernels. These are the only thing you're learning in your CNN. There's no other parameters. So at test time, if you apply those kernel on a size of 200 by 200 or 2000 by 2000, it doesn't really matter. Like the CNN, I mean, yes, the object recognition may be not as good, but for the purpose of the CNN itself, the only thing it learned is, oh, there's a template I'm looking for, like 13 by 13. This is what I've been looking for in the image. So the nice thing is, even if you had trained your CNN on images of 64 by 64, there's nothing that stops you at test time to run it on 640 by 640. Your next response map is not going to be going from 64 to 32 by 32. It's going to go to 640 by 640 to 320 by 320. So the response map will be bigger, but the behavior of the CNN is the same. And that's why the fast RNN is able to do that, is you could train on a small 64 by 64 the same way that the CNN was trained previously. But at test time, you can run it on the whole image and run it a second time and run it and store those response maps. They're much bigger than what is needed. And then you have the algorithms, which I can give an intuition again, how it works. But you have a second algorithm that says, hey, these are the region of interest. And these, for now, suppose that all the region of interest are 64 by 64. Then, yeah, it tells you 64 by 64. Now you can go and crop the response map. Cropping is very fast. Running again the neural network every time for each region of interest was really slow, but doing it only once and just cropping the response map. And then at the end, when you get maybe you go 64 by 64, 32, 16 by 16, at that point, you can simply have your fully connected on top of that. There's a little bit of trick to allow region of interest that are not 64 by 64 by doing some padding and things like this. And these details, I don't think they are as required, but that was the intuition. I know I went a little bit quickly, so there were a few questions about that. So that's the idea. CNN that is trained on 64 by 64 can be applied on any size, because the only parameter of a CNN are those templates you're looking for. The second question was like, how do you find those region of interest? And there are many approaches. The one that I talked about was superpixel. What is this? Is you should say the beginning, every pixel is a region of interest. Every pixel is another, and you're slowly growing them because pixels look the same, and you're slowly growing, and eventually you get region of interest by having coherent patches of the image. But there's a lot of other approaches to find those efficiently. It's also related to what's called image segmentation. So I wanted to share that. If there are other concepts, often is the one at the end of the lecture when people are both tired and maybe we're cramped over time. So please ask these questions. I will do my best the next lecture to discuss them. And if you have still questions on this, happy to go in even more details. Yeah. What I said about segmentation, but segmentation it's not exactly segmentation, but if you had perfect segmentation of the image, then yes, region of interest will be clear from that, because if you already completely segmented all the object in your image, then you can, what are the region of interest? There's some rule-based approach that could go on top. So I don't know how I phrased it last time, but yeah, segmentation comes early. That's one of the early stage. A superpixel is just one way to do image segmentation. They're the kind of related approaches. Yeah. Okay, great. You should have yesterday all selected your one of the 6 papers, and the survey, your summary are needed by Friday. And then you have until Monday to have 3 extra posts. And then a post could be a question you asked for another survey, a summary, or also responding at questions for your own summary. And all of this gone. I mean, you can do more than 3, but as a good student, let's just do 3. That's the minimum. So like let's do at least 3. That's the goal to answer. And the real goal is to learn. You have 4 papers, but you've read only one of them. So try to learn. We select those with care. At least that's where we take quite a bit of time selecting those papers. Okay, today at 10:30, we'll have a team matching event. We looked at all the forms, and we had a very scientific algorithm, a clustering algorithm, patented to look at this. We did our best to do an initial clustering to say, hey, these are similar interests, but this is very approximate. But the idea will be to allow you for 15-20 minutes to discuss with other students, and also the TAs. We have 4 other TAs that are going to come if you have any questions about it. Remember, by Wednesday next week, we would like to have most of the teams all complete. If for some reason you have not a team by that time, you should still submit a pre-proposal describing the kind of project you would like to do, so that we can help for the final match if needed. Okay? Great. And AWS credits, it keeps changing from year to year. We used to have coupons of $50, and we could have a few more for student. Now you get 150. That's it. There's no more. All students last year we didn't have any problem, but we also ask teams to select their project accordingly. So if you don't have access to any GPUs and you're only going to rely on AWS, don't go and select a project with video, for example. Video processing requires a lot more GPU time, and so select something that have images and text, for example. There are plenty of them, so there's a lot of really interesting work there. So just be adapting to what resources you have in your there's the equivalent. There's Google Colab that many of you probably know, and Amazon also had their own version of that. That gives you for development. So the 150 should really just be for deployment. Like you have your experiments, you debug the model, and you just want to run it. That for the development, we highly suggest to use one of these platforms that gives you a GPU for free. So that seems to work well. Okay, today we're talking about unimodal. That's the second part of a two-part series on unimodal representations. The goal is to discuss now another modality, this time language modality. We'll focus on it as a word representation, sentence representation, and also understand the structure of language. Now, there are many courses on this topic. I'm kind of giving a full 14-week course in 20 minutes, so it's very high level, but happy to answer any question. I will really highlight 2 or 3 concepts that are very fundamental, because now these days when you hear GPT and all this, they all train almost with the same intuition of 20 years ago about distributional hypothesis. It's like they're all based on the same concept, and we've been building from that. So it's very useful to understand the basic concept, and then after that you can build from that. As we talk, the simplest way to represent a word, and often these GPT and BERT and all this, they still take as an input a one-hot encoding for each word. For each word will be out of 300,000 something words in English, or as we discussed, it could be a token, a subword level, but still there's a dictionary. So that's going to be the input, but that representation is not the most informative. It's very sparse. So is there a way to get something work? So could anyone explain what Bardawak is? No? I thought, does someone speak that language? Bardawak? No? Okay. Okay, then I suppose we'll have to go. Bardawak, he handed her a glass of Bardawak. Oh. Probably start understanding what a Bardawak is. Beef dishes are made to complement the Bardawaks. Huh. Come on, start speaking the language, huh? Okay, slowly learning. Nigel staggered to his feet, face flushed from too much Bardawak. Okay, now you're getting an idea of what Bardawak is. Malbec, one of the lesser-known Bardawak grapes, responds well to Australian sunshines. Oh, okay, now and I dine off bread and cheese is excellent Bardawak. So what did you learn about Bardawak? From the first one, probably a liquid. It complements something you can drink, something, and then probably something related to alcohol, flush down. So the idea, the very core idea of GPT and everything before it, starting to very simple statistical approaches to what was a big moment, aha moment, which is called word2vec, which I will discuss in a moment. The basic idea is that the context of a word, you've never heard Bardawak, but the context of a word is a good approximation of its meaning. That is extremely important. That's what is behind this approach of training a large language model like masking, is the idea that if you know the other words around, and if 2 words have the same context, they're likely to have the same meaning. That's the basic building block. I may not completely understand what the meaning is in itself, but I know that all of these words have the same context, so they must have the same meaning. And that's the core building block of most large language model that we have. And that's what we'll call in a second, that's called the distributional hypothesis. But yeah, by just having the context, not knowing what Bardawak is, it's made up. It's not French. It's not anything. It's Bardawak. It's made up. But you learn a new word. And you learn that it's heavy alcoholic beverage made from grapes. All this from the context. So if next time you see another word, maybe wine, in the same context, then you'll be, okay, these words are close to each other. So the distributional hypothesis approximates the meaning of a word by its surrounding words. Statistics about which other words are seen around that word will tell me a lot about that word. So words used in a similar context will lie close together. And so running, walking will often be used in the same kind of sentences, so they are related to each other. And the way to implement it before the neural network version was statistics, which is really cool. So take all the words, all the verbs in the English dictionary, okay? Or let's take, in this case, 6 of them, and let's try to find a really good representation of all the nouns in the English dictionary. So the idea is, depending on how often a noun is seen with one of these verbs, will tell me its meaning, will be a way to encode the meaning. In this case, so knife, may see it with get, with see. You rarely hear a knife, although you could hear it falling. And let's not get to the kill. So cat, dog, don't ask me why they come here, but boat and all this. But yeah, so all of these, the verbs, which verb goes with which noun, tells you. So this becomes a signature. It's a signature. And what's cool of this statistical approach is that signature has, in each dimension, has a meaning, in a sense, because it's how often it comes with a certain verb. The difference with GPT and all this, they still have this 500 or whatever, 400 dimension vector. Unfortunately, the dimensions are not as meaningful. We don't know, oh, the first dimension is about like how often it is with that verb or that. But if you look closely, some people try to analyze, there is a pattern on what those dimensions could be, but it's not as clear. In this case, because it's directly in a co-occurrence matrix, then we can use these vectors. And so that's the first most important thing. The context can approximate the meaning. The second one is, let's use that as a vector. And the question would be, I have two vectors. How do I know that they are the same meaning? The first idea would be, hey, if I have two vectors, let's say one for dog and cat, one option could be just Euclidean distance of those points. But what is this telling me, the Euclidean distance? Why is dog different than cat in this case? It's just because dog happen more often than cat, okay? So if you take the vectors themselves and just look at the counts, that doesn't help me. Now, if you normalize it to 1, then you can compare the Euclidean distance. The other way to do it without normalizing or doing the normalization in a different way is, instead of looking at the distance, you can look at the angle. And that's why for a long time, and still now, if you want to know if two embeddings are close to each other, you often end up using the cosine similarity. It's just a nice way to, in a sense, normalizing the vector before looking at the distance between them. And then that one makes sense. It's either you normalize or you look at the angle, and the angle tells you it's going, the proportion of how much I use each verb is similar. And that's what a word embedding, a sentence embedding, a GPT embedding, what does it tell you? It tells you, if I compare with some referential, and you could say magically GPT decided of 500 verbs. It's not exactly how it's implemented, but if it helps you understand how GPT is working, it decided of 500 verbs as the most important to describe all the other words, and then it just decided these will be my references. The reality is that it doesn't decide of one specific word, but more of a direction. You could say an average of words in a sense, as their basis vectors, and all other words are compared to that. This is completely true for what's called word2vec. When we're going to start talking about GPT and others, it does a little bit more than just this intuition of the distributional hypothesis. It will also do contextualization based on the meaning of other words. So we'll talk that in a second. But for now, when you think of it as just embedding each word, that main thing it's doing when you do masking is saying, hey, how can I approximate the meaning of a word by its context? I could stop now, and I'm done with 80% of the core aspect of the neural network. But let me show you how this is done in practice to implement this intuition in a neural network. So this intuition will be implemented, but instead of counting the core occurrence directly, here's the key part that happened around 2010 is word2vec. Word2vec was in fact a very simple neural network, a one-layer neural network. We still call it deep learning, but it's not deep. It's one-layer neural network. But the really interesting intuition is to, instead of counting words to create that vector, is to make it a prediction task. And here's the prediction task: is that I will take a corpus, a large English corpus of sentences, and I'm going to do a prediction task. On one side, I have all my possible words in my dictionary, all the possible words in the dictionary, okay? And for any sentence, so let's say I have a corpus of 2 billion sentences. For each sentence, for each word in the sentence, I will create one entry in my training set. Okay? So if you have 2 billion, I mean, at the end, you subsample. I mean, you're not going to sample all of it, but like you have 2 billion, and for every word, you have one entry. And that entry will be a one-hot encoding of that word. And on the other side, we will have all of the, it's a bag of words of all of the context. Okay? So my data set, my training data set is a bunch of sentences. You could say randomly, I select maybe 300,000 of that data set. And then I have the word and its context. And I have it repeated 300,000 times. That's my training set. And the idea is I'm going to train a neural network to predict from X to Y. From a word, try to predict the context. By trying to predict the context, I'm trying to mostly predict its meaning, because the context is an approximation of its meaning. And because that same word will come often, like we'll by design not select words that are not happening at least more than 10 or 100 times. There is a little bit of a tweaking there. Because that word will happen often, then in a sense, by predicting it over all of its context and averaging, it's a simple loss function that average over all those contexts. The loss is mostly taking the average of the context for that word. It tries to predict the average of that context. That's really what it does. So how do you train that? A very simple neural network, one layer. In fact, the first version, I think, had no nonlinearity, no activation function. It was literally two matrices. The first matrix, well, you could call it the encoder matrix, that goes from that 100,000 to that small, maybe 300 dimension. And then that 300 back to the context that you're trying to predict. And so that was the first word embedding. And for 5 to 6 years, this was the main way to encode most of language. The 300, you could say, is those 300 verbs, in a sense, that are representing each word of the English dictionary are used as a basis. But in practice, these 300 are maybe something different. Maybe it's one of the dimensions is more about positive, negative, more about the future and the past. Unfortunately, these are not as interpretable as we hope, but still they're very powerful. Trivia question. If I give you this magic thing, neural network, how do I use it for encoding a word to one word at test time? Do I need both matrices? Okay, no, I only need this one, only the encoder. How do I encode a sentence? For a while, the way of encoding sentences was just to average the words. So I encode every word and simply encode it. Now, there are a lot of issues with this, but still, it kind of got us 80% of the way. But there was a lot of issues. What do you think are the kind of issues you'll have here? At least 2 or 3 issues. Yeah.
When you average the words, you're kind of mixing the embedding into the issue.
Yeah, so if they have a word like plant like a factory or plant, like there's more than one context in which you can use the word. So in this case, the same word could have more than one meaning, and then they end up just being average in this situation. So antonyms were a lot closer than you would think. Yeah, 30 minutes. So this is some of the issues, and like for 5 years, we'll like go and like try to improve on that. But they were working really well. So they did get a lot of mileage of it. So to encode, yeah, we would, instead of encoding as a one hot, now you take a vector, run it through this encoder, and that will nicely give you that 300 dimension. And then you can compare these with cosine similarity or by normalizing the vectors and Euclidean distance. And there were some cool things. This is a cool thing that will also come later when we talk about multimodal, because the multimodal version is even cooler than that. But they're not, because they're in the same space. All my words are in the same space. Then there was a question of like, can I even do arithmetic with it? So if I take the king minus man plus woman and then get a vector, then you can sample what are the closest one in my training set. And yes, things like queen will come out, words like queen. They did the same for like word China, and they look at pair of words and see if it seems that the same direction from a country to its capital. There were a lot of good things, nice things there, but there were a lot of issues. Some of them we discussed, and some of them we did not. So like biases would be another issue in these. That's still an issue in many language models, but programmer minus man plus woman, homemaker should not be the answer or the closest to that. So there were a lot of issues. And so now to address some of them, the idea is let's not just encode words by themselves, but also encode words as part of their sentence. And so for now, before I get into the language model in a second, I will just talk about sequence modeling. How do I use this kind of embedding, but now to do some tasks? and there's different tasks you can do in NLP. There's at least 3 or 4 that I want to highlight. The first one is a sequence prediction. Every word has a label, either because maybe you do part of speech tagging, trying to find like noun, verb, or maybe you're trying to find the sentiment of every word. Or you want to predict specific entities or name of places, name entity recognitions. So there's a few tasks in NLP where the goal is to recognize for each word. And the idea there, and I used to have like 1 or 2 lectures on RNN, on recurrent neural network. We removed that to 2 slides at very high level. Happy to tell you about LSTM and all this, but we're not going to go in detail. But the idea here is that instead of making prediction of every word separately, I would like to have some kind of continuity in how I make my predictions. And for a while, the way to do it was to do it with models that are, in a sense, directed. There is a sequence and there's a direction in the sequence. Most recurrent neural networks have a direction, they're directional. I'm emphasizing that because now with transformers, we decided to connect everything with everything. And so there's no more of that directionality. But in this case, a lot of those were in fact simple neural network with a recurrence that was added to it. And work will be in fact the loss for all the words. And we talk about CNN having tied weights. If you remember tied weights, we talk about it for the RNN, the CNN. Same thing here for the RNN. The weights that goes from here to there, like these neural network that will go there, will be tied to the weights here, tied to the weights here, tied to the weights here. What it means is instead of training a neural network that has a different set of weights for the first word, for the second word, for the third word, no, the neural network sees every word the same way, the same exact way. The only way it knows that it's a different word in the sentence is because it will have knowledge of how the previous words were embedded up to now. And that's the information that will be shared between there. So this tying of the weight, when you have your neural network that goes simply, so this is the input, you will have your output, your prediction, and you have input in middle layer. These are your weights. And you have your prediction, and you have your ground truth, and then your loss is simply comparing the prediction to the ground truth. This is just a typical neural network. In the case of the RNN, the idea is simple: is that you have a little recurrence, you have a new set of weights, and then it's easier to look at a recurrent neural network when you unroll it. So this is a neural network. And the recurrent neural network, the only difference with the normal neural network is these extra weights that will link time t to t plus 1. And this can be seen when you unroll it. But as I told you, the weights to go from here to here, what are they? They're exact same as here to here. That's tied. So these are the same weight. The weight that goes from the latent layer to the prediction is the same. This is tied. And the only thing is that now I have weights to go from one recurrence to another, but again, they are tied. So the weights that goes here is also tied to here, is also tied to here. I'm not going to explain the backpropagation in detail, but I want to give you one intuition, which is the following. Is I find some error during training because there's a loss, there's some error here. I backpropagate this error. When I backpropagate this error here for this V parameter, how is this affecting V? How is the error affecting V? How is this error affecting V? How are all these errors affecting the V? because they're tied, because the weights are tied, you simply add the errors. Okay? So the error that were identified at this time t will be added to the error at t minus 1, at t minus 2, at like all of these errors. The back propagation is the same. It's just that there's a little bit of trick to add the errors with each other. That's why tying. And the recurrent neural network was the same idea when we're tying the weights. At training time is really where the tying is happening. Okay, recurrent neural network in 2 slides, very high level, but the key aspect here is you have that recurrence that goes on, and these weights are in fact tied with each other, as I just explained. Same parameter model. So now if you have a sequence of 300 words or 20 words, it's all the same models, all the same model parameters that are used. So how do we do it now if I have only one label for the whole sentence? So the simplest, there's been a few approaches for this, but the simplest one is to say, hey, I'm going to do the same model as earlier, but my loss is only going to be at the end because I have a recurrence. It's a directed one. In theory, the embedding at the end is the one that includes all of the previous embedding. In fact, I don't even need that part here. There's only one label there. Now, there's been extension to that. So in this case, the loss, as we talked, will be simply the loss here of how well I can predict at the end. But then we will now take this to the language model. And I have to explain one thing. We called, and it's an obvious thing now, maybe because it's been in the news so much, but I just want to emphasize, language model doesn't just mean it's a model that uses language as input. Okay, that was my first intuition when I heard language model. Language model doesn't mean it's a model that uses language as input. No, language models were designed and created in big part for speech recognition. And the idea is I want to improve speech recognition. Let me look at the sentences in the English dictionary and English corpus, and let me try to predict the next word. If up to what I've seen, can I predict the next word? And I will use that predictor to help improve speech recognition. I will show you in a second. So the language model is not just a model that just in general, although these days we started using language model as like just a model that takes language as input, but language models were trained and still now are trained with the idea of predicting the next words. In fact, GPT, its strengths, although there's a lot of little magic on top of it, but the basic building block, why is it ChatGPT able to answer, is that it's seen what the question was as input and then decide what the next words or series of words will be. So prediction of the next word is the core building block of language models. In fact, as I mentioned, they were designed for speech recognition. So speech recognition, the idea here is I want to predict what are the spoken words from the speech signal. And here, there will be two main components to speech recognition. Again, it's a very high-level view. People in speech will say there's a lot more than just two main components, but there's like two primary components. One is simply trying to predict from the speech each word almost individually. So from like you could say from the vowel, the sound of the vowels, almost predicting the vowel, the spoken syllables. The word, this is where the language model comes in. The language model will say, hey, this prediction you made based on what you heard, that doesn't sound like English. Okay? This is just a nice prior, and that prior you can compute in a nice recurrent way, that language model, that's a key aspect here. So that's from looking at just the acoustic and the word, but this is just saying how is this language, how this sequence of word likely to be. And to compute that is just rolling. So I thought I had a sent. Oh no, I did put the equation, but the equation of that can be anyway. It would be probability of the word, the first word by itself, time the probability of the second word given the first word, time the probability of the third word given the first and second word, and then you unroll like this. So that's why the core building block of this is that probability of the next word given all the previous words I've done. Now, back in the days, we didn't have the computation we currently have. So instead of using the last 200 words, we'll often only use the last 2 words, using bigrams and trigrams to just compute that explicitly. In fact, counting that bigram and trigram is literally counting those probabilities. How often do I see this word, given that I've seen those 2 words before that? So I said it. It would be interesting how often at the end of this class I say it. But in my days, that the bigram and trigrams were still the way to do it, to do a language models. And I implemented a trigram model as well. So there was a simple statistics, but very useful. Now the language models, and that's one thing you will see as a characteristic of a language model, is how many words or how many tokens it can take as input. I don't know the GPT, but it's now in the hundreds, maybe even the 1,000 in the next generation. So it's a lot longer the context they can take. So the way you will be able to predict the words, in fact, is with an RNN. You can do now by counting the probabilities, but you can also make it as a prediction task, as a neural network task. And the key thing is that you need a special token, a start token. And then the start token would then give you the next word. And then given the encoding of the previous word, you get the next word. So the task is the same as a prediction sequence labeling task. Is just that you're learning a neural network that predicts the next token based on the previous tokens, the previous words. It's cool because you can train this. It doesn't sound useful because why would you train that? But it's really nice. You don't need to annotate data set. You just need a bunch of sentences and just have sentences and have them. And in fact, you take every sentence and shift it by 1 word, and that becomes your training set. And now by training that, what you get is now it starts being really cool because suddenly you have an embedding of the sentence. This embedding here is a sentence embedding. It's a representation of the sentence. And there is this. You're probably wondering, you probably heard about BERT, but only a subset of you probably heard about ELMo. It was a very short-lived, in fact, by the time they got their best paper award, they were already not the best at that point. So this is one of their shortest-lived best paper award at NACL that you've seen. Yeah, but yeah, what they did is take this idea, scale it up with a large data set, and just do a second step of bidirectional. So you encode, but you train not just one model, but you train a second model the other way. And your embedding for the sentence is just going to be those 2 vectors. And that was effectively, ELMo was trained that way. So the way to train it, I said originally the way to train it was to predict every word. ELMo, it was short-lived, but it did 2 things. One is it did the bidirectional, which ended up being completely killed by the transformers and the self-attention, but it brought the idea of masking again. And that one is still used now. The masking is still used, and masking is just distributional hypothesis. That's what it is. Masking by saying, hey, I will give you a sentence, I mask a word, and I want you to predict that word. I want you to have as high probability as possible for that word and as low as possible for the other words. That is back to word2vec in a sense. It's the flip. In a sense, it's a flip version of word2vec. You're kind of taking the context as input and predicting the word. Word2vec was going the other way around, predict from the word to the context. Okay, but it's just a flip of this. So yeah, ELMo was this pre-trained large language model. And that's when we started using, I never thought we would use the pre-trained language model longer. It didn't sound like a catchy name, but we're still using now pre-trained model. That was really exciting, is that the same language model trained on a large corpus was able to be applied to new tasks. So a lot of few shot, zero shot came around that time, was really interesting. So le chien sur la plage, the translation could be done because now I have my encoder and I can use it, and on top of that have an RNN that takes as input that context from that first language that was trained and learn to predict the second language. And the loss function here will be the prediction from that target language. So in this case, it will be English. So take the French, train originally French by itself, the language model, but then you can use that with a decoder that is trained with a corpus of paired data of French and English sentences. And coming soon, in about 2 weeks, we'll go in depth in transformer, which expand this idea of bidirectional to mostly connect everything with everything. That's the core idea there. I just want to use the last 10 minutes for giving a very condensed version of an NLP course, NLP 101. Just the basic parsing. How do we take language? What's the beauty of language is that it was created by humans. So there is a lot of thought on how, or you hope at least that there were a lot of thought when they were created. There's whole institutions that think about languages, how to adapt them over the years also. But yeah, so sentences have a normal structure in that, and that's beauty. And that's also why I highly suggest to have language as one of your modality, because it is human created. It has this natural structure to it, and it can help you structure any multimodal problem. Now, you can do it with other modalities, but if language is there, it can often be used as the backbone for the fusion. At least this is definitely a baseline model you should study. So what can you tell about this sentence? Alice ate yellow squash. Very simple. But so from there, you can do what's called part of speech tagging, just finding out for each word the tag. So a noun, a verb, adjective. This is one very simple way of parsing a sentence. I'm going to present 3 approaches, which I would say are at least 3 basic approaches that you should at least know about. The 9th one on top of that is to look at phrases. Sometimes you hear sentences and phrases and you think they're the same. No, they're not. So a phrase is usually often referred more as either noun phrase or a verb phrase. So here, in this case, yellow squash are together. This is a noun phrase. This is an entity. It's a squash with the adjective yellow. It's a noun phrase. Now, the verb phrase will be the verb that is associated with this noun phrase. So in this case, ate the yellow squash. And so when you do this kind of parsing, where you identify both the noun phrase and the verb phrase. There's different way to do it. Some people will call it shallow parsing, where you're trying to find the start and end of all your noun phrases. But then there's also a way to take this noun phrase information and put it in a graph. And that's a type of parsing you'll have, which is called phrase structure grammar or syntactic parse tree. The idea here is you're trying to identify, in a sense, what are the small coherent entities, we'll call them noun phrase, and now relate how those noun phrases are hierarchically related to each other. And so that can be done in this kind of representation. Thus, these are equivalent in this case. So you will sometimes see these parse tree and be like, oh, where did it come from? It comes from noun phrase identifying noun phrases. I want to bring a second one, which is cooler, but doesn't always have that nice perfect tree structure, although you can force it to be a tree. And that one is called dependency parsing. There, you're not only looking for noun phrases and how they relate to the verbs. Here, you're literally looking at how a pair of words relate to each other, how they relate to each other. And so for the type, and there's a bunch of those tags, but the more obvious one, the subject of a verb. And so often this parsing will often start with a verb, the primary, that will often be the root. And then from there, you can have the object of the verb, and then you could have an attribute to the noun. So now I parse it, but it's different from I'm not looking for noun phrase and verb phrase. Now in this case, I'm looking at dependency between words. Which word relates to each other? This is, if you have at a very high level, at least understand these, because often in papers we will look at like module network, when we look at neurosymbolic approaches, they will often try to take advantages either to the phrase structure grammar or the dependency grammar as part of extra information. So the really nice thing of this, why would we even care for that? Is it not enough to just get language in a sequence and all the words? And it was at least it's debatable now with those very, very large language models. I think we're at a point where those large language models are handling a lot of this parsing automatically, and a lot of the disambiguation that I'm talking about seem to be handled quite well with those large language models. So we don't see it as often, the parsing, but I want to offer it because there are often some ambiguity, like can be both a verb and a preposition. So then you want to disambiguate the use of the words, and this disambiguation will be often by looking at the parsing of it. Around can be also be a preposition, a particle, or an adverb. So all the same word we talked earlier about word to vec, the same word can have different meaning. But not only that, but the same word can have different function in a sentence. And you want to be able to handle that as well. So language ambiguity, a typical one. Salesman sold the dog biscuit. Okay, so you probably, because of your language model in your mind, so the salesman sold the dog, like depending where prosody can come in really nicely. So salesman sold the dog biscuits. Salesman sold dog biscuits. Okay, prosody was useful, huh? Multimodal. Okay, so the parsing of these two are quite different. In one case, and is in the noun phrase is dog biscuit, but you could, doesn't happen really often, that you sell to a dog a biscuit, but you could. And that's the difference there of the parsing of this. And that's an example also how prosody can help disaggregate some of these situations. So as a summary, you have some examples. So part of speech tag, the constituency parsing, which I also call phrase grammar, and the dependency are three examples of parsing that you can look in this. And you can think of how does neural network, and we'll discuss that in about 3 weeks, 3 or 4 weeks, to take advantage of that as you do parsing. And some of it is now under the umbrella of neurosymbolic, where you're trying to do not only everything in dense representation, but also have a more discrete way of modularized way to do things. The last thing I will present is everything I talked up to now was sequences, but the RNN can be modified very slightly to also handle a tree representation. And that's really cool. And the key idea is these purple one, oh, I'm missing an arrow. Okay, sorry. These purple one, the key idea for there is that they will take as input 2 of them. So I'm only going to be able to handle binary trees with this kind of recursive in the neural network. But if I do that, these will all be tied. So the way the information is integrated here, the way the information is integrated here, the way all of these are all integrated the same way, and they're integrated with a neural network like this that takes as input 2 embeddings and output only 1 embedding. So I have 600 by 300, that neural network, and that allows me to then train a neural network. And maybe here I have a label at the end. Yep, 10:30. Oh, for this class, there will not be a third segment. We'll give you 2 points automatically for the third segment. Enter something because it's required in the form, but just like no need, because the last 20 minutes will be used for this. But yeah, so that's the idea of using this recursive one. I put some resources. This is a lot for the old, I would say, technologies. I just want to emphasize one, which I still love very much. And it's the lexicons, because it's interpretable. It's a representation of language where each dimension has a representation, like has a meaning. And the meaning in this case is done simply by having a dictionary of categories. So categories could be positive and negative, or it could be about topics family. So each of the 84 dimension of my embedding will have a meaning. And so this is a nice approach if the kind of data sets you have are data set where you would like to do analysis afterward. There's extension of that. One of them is even from our own group called Santacon that brings this, but with a large language model as well. So, but the interpretable representation are good to have.